I don't remember how we did geography.
Let's do rule of 72, doubling time. It's a doubling time estimate. It's not 100% accurate, but it gives you a decent idea. Okay. The rule of doubling time. The rule of 72 states that the number 72 divided by your AIR, or what we call our annual interest rate, is equal to how long it will take to double, approximately your doubling time. So, let's say the annual interest rate. The world's population is about 7 billion, okay? And the annual growth rate, I think is like 0.01%. It's like super small, but let's say it's 1%, okay? Just so we have an easier number to work with. Actually, no, let's not do 1 because that's getting a little too easy to divide. Let's say it's 3%, so it's way, way, way higher. All of a sudden, there's this huge growth spurt, okay? So 3% growth rate, or annual interest rate, if you want to call it. Annual interest rate. And I put too many L's, but that's okay. So let's use that. So pretty simple to calculate. We have our doubling time is equal to 72 divided by 3. So we divide it by 3. And, we're going to get 24. That's right. Okay, so apparently, according to this, it'd be 24 years for this doubling time to happen. Okay, so we can make a compound interest. It has to be compounding interest. So if you guys remember the formula for compounding interest, it was the future amount is equal to the P, the present value, or the principal, whatever you want to call it, 1 plus I to the power of n. So we're going to prove this. So our future amount, our A, is double what our present amount is. So our present amount is 7 billion. Okay, I'm just going to write 7B because I don't want to have to write 9 zeros after. Okay, which means the double amount would be 14B. You just multiply it by 2. Okay, and I'm going to show you how we'll be able to reduce that just 1 and 2 in the future here. 1 plus our interest rate. So the rate was 3%. And the compounding period, in order for this to work, it says in the rule that it needs to be compounding annually. So the compound period is 1, which doesn't change anything. When we divide it by 1, nothing changes. So 0.03 divided by 1 is 0.03. Our n. Our n is normally years times compound period. Years times 1 is still years. So this n is, when we isolate, is just going to be the number of years it takes. So we're going to isolate for n. So first step to isolate for n, we'll take this multiplication, this 7 billion, and we're going to move it to the other side. So it'll become 14 billion is equal to 1.03 to the power of n divided by 7 billion. We brought it over and we divided. And 14 billion divided 7 billion is just going to be 2. So essentially you're looking for doubling time. That's what 2 stands for, how long will it take to double. So 1.03 to the power of n. Now, I got to bring up a point here. The log of both sides. So just like in any equation, if I was to multiply one side by 2, I'd have to multiply the other side by 2. In this one, we're putting things to it's like a type of exponential function, a log. We're going to put both sides to the log, okay? So I say log 2 is equal to log base 10, and we don't write a base for base 10, so you don't have to worry about it, of 1.03 to the power of n. Now, the whole reason we do that is when we put something to the log, any exponents, that's not the thing I wanted, there you go, any of the exponents, there it is, can be brought down and put in front of the log as a multiplication. Okay, so now we're not stuck with an exponent. So to simplify just the right side, the left side is still going to say log of 2, log base 10 of 2, is equal to, and now I'm going to put the n in red. Now we'll put it in blue. So now it's n times log of 1.03. So though I wrote this step in here, you can go from here to this step right here, where we just say log of this number and put the n in front like it's multiplication. Okay? The whole goal of this is to isolate for n. So I need to divide this side by log of 1.03. I'll do it to the other side too. Essentially, to move it over, we have to divide by it. So the next line will read n is equal to, and again, you don't always have to write in red, but it's just something different. So log base 2 or log base 10 of 2 divided by the log of 1.03. So maybe you've never really used this on your calculator before, but that's fine. It's going to give us a nice, accurate answer to see how good our doubling time truly is.
Wait, what's the difference of like what does log do? Because could I just do the same thing, like 2 divided
it
by
helps you
1?
isolate for like exponential functions.
Oh,
That's the
okay.
whole point of it. Yeah. So log of 2, and it'll say log 10. Like technically it's the base 10 if your calculator puts it. Okay, but it's log base 10 of 2 divided by log base 10 of 1.03. Okay, so this is going to give us our true doubling time here, and our true doubling time is 23.4 years, which our rule of 72 was pretty close to 23.4-ish, approximately 23.4-ish years. So our rule of 72 for doubling time is really good. 24 years, yeah, that's pretty much what it was. It's a little bit, a couple months after that. And you clearly had to do far less work than you had to do with your logs on this side. But if you're not doing doubling time and you're isolating for n, then using the log will be much faster than trial and error, and it'll get you the exact answer every single time. Even trial and error